Someone asked me about the principle of orthogonality, that it is only proven for real things, or it's only proven for the real part. So first, let's complete a more general proof of the principle of orthogonality. We know that using the condition that not this. So the condition that this sigma square equals 0, we get
Sir, could you zoom in a little bit?
yes, better.
Yes, sir.
Yeah. So when once the laptop starts, once the laptop logs in, I should be able to write again, but that thing simply refuses to log in despite my best efforts. So yeah, we'll see. So this is 0, or expectation of this times W minus U n minus 1. Right? Or
Sir,
yeah.
sir, what is this U? It is same as that X.
Oh, sorry. Yes, X. Sorry. I since this is a different platform and we were using X.
Yes, sir. We were using X.
Yeah. Now this looks okay.
Yes, sir.
Yeah, fine. So
Except that there should be Hermitian, I believe. Hermitian and vector
yeah, there
notation.
should be a Hermitian after the second one. Fine. So this Hermitian shouldn't be boldface. Fine. Or
Yes, sir.
I can take the expectation as common, and expectation of
Sir, X conjugate is not a vector, right?
yes, X is not a vector, so let's not make it boldface. Fine.
Yes, sir.
So the bold faces are vectors and non-bold faces are scalars.
Scalars. Yes. So in while writing by hand, I use underlined as vectors and non-underlined as scalars. Or station of x n minus 1 times minus eta n equals 0. Fine.
Yes, sir. Sir,
Or
the W here is the W optimal, right? I mean,
yes,
we are
it will be W optimal.
okay, sir.
Let's do it this way. Or laptop has logged in. Now
Sir,
it's still stuck. Yeah, Shubhashish.
sir, if the laptop starts working, can you use that one? Because slightly it gets confusing due to
Yes,
the.
yes. I will start using the laptop as soon as it's usable. All of us know
Yes, sir.
how irritating laptops can be when you need them and they don't want to work, right?
Yes, sir.
Yeah. So let's have patience with that thing. I don't want to reboot it too often and then it lands into some other problem. Mm, I don't know why laptops get desktops never get stuck. Only laptops get stuck. I still haven't figured out why. Anyway, so this is 0, which means that when we achieve the optimal, the estimation or the prediction error, estimation error or the estimation noise is orthogonal to the input and this is vector, sorry, and all of these right hand sides should be vectors. All of these should be vectors. So, yeah, the input vector, that is since the estimate is a linear combination the estimation to the estimate. Uh, this proof is okay for the principle of orthogonality.
Yes, sir.
Fine. Rahul, is he here? First of
Yes,
all,
yes, sir.
yeah. So this proof is okay. Samarth asked it, right? Or you
No,
asked it?
I asked it, yeah.
Okay. So this is fine.
Yes, sir.
Excellent. So let's move on. So this actually completes our discussion Now let us move on to the second topic of the course, that is signal spaces. So what color? Red, and let's make this boldface. So signal spaces, or how to represent signals as vectors. So to answer this question, that how do we represent signals as vectors, or what are signal spaces, we will revisit vector spaces, and I will start out by typing the definition of a vector space. So a vector space is a set of elements called vectors with a set of rules for yes. So am I audible? And is the screen visible again?
The screen is
No, sir,
not
the
visible,
screen.
but you are audible.
Okay,
Yeah,
great. So
you're audible.
I got disconnected. So this is one of those days when पूरी कायनात हमें क्लास लेने से रोकना चाहती है. Anyway, so fine. So a vector space is a set of elements V in V called vectors with a set of rules on for operating on these vectors. The laptop is still not up. And let and scalars alpha so this F is called the field of scalars. Right. And a vector space is with called real space and one with the lex space. Note that I have not defined a vector space in terms of Rn or Cn, as is the convention. Fine. Now, for a set or script to be, laptop is still misbehaving, so I will yeah, now it should work. So OneNote and Teams. So I will switch as soon as possible. For a set V to be a vector space, it must satisfy the following axioms. Whereas the first axiom is 1 for each closure. You know what is closure?
Yeah, like basic operation, addition, subtraction. Even if we
No.
do, no,
Yeah.
even if we do that, it will remain in that same
Yes.
set.
For each, yeah, or for all u comma v in uh, unique exists.
Sir, U plus V belongs to V, right?
Huh? Yeah,
U
sorry,
plus
V,
V.
not F. Yes, my bad. Exists and is called the sum of u and v. Join now. And yeah, the laptop is up. So don't have to do much. In another minute, we should be up. So let's take a minute's pause, I believe.
Okay, sir.
So we'll pause for a minute. Meanwhile, I can switch here. And so share screen, screen 1. And this is there. And this is there. Fine. There's slight lag. There is lag now, but you will have to bear with that, unfortunately. So visible? First question.
Yes, sir.
Excellent. So let's So call the sum of u and v, and then yes, sum of u and v, this satisfies A or 1A commutativity, that is u plus v equals 1, 2 associativity u plus v plus w equals fine. Additive identity. What is what is, or there exists an additive identity. There exists an additive identity 0 in V such that V plus 0 equals V for all V in V. D additive inverse for all V in V. There exists a unique minus V in V such that V plus minus V equals 0. Fine. Then the second property is, or multiplication by scalars. Here for all alpha, okay, I used so in my notes I have written this f as double f instead of script f. So for all alpha in f and v in v, alpha v is contained in v. Fine. This is closure over scalar multiplication. Alpha beta v equals alpha times beta v. Associativity. Over scalar multiplication. Fine. Existence of multiplicative existence of multiplicative identity. That means there exists one f such that 1v equals v for all v in distribution over addition or distributivity over addition, which means alpha u plus v equals alpha u plus alpha v for all alpha in f and uv in v. Distribution over multiplication, which means alpha plus beta u equals alpha u plus alpha beta in the field f and u. Fine. This is just a quick recap of the properties of vector spaces. You might have covered this in greater detail in your linear algebra course. And you might also know that trivial vector space, this the all zero vector or this additive identity, this is called the trivial vector space. You agree with this? Is the all zero vector a vector space?
Yes,
So
sir.
isn't it a null space?
Yes.
Sorry?
Yes, it
So
satisfies all
want
the
the all
properties.
zero
Yes, sir.
vector? Yes, sir.
Shubhashish, you are saying something else?
So I thought that zero vector is part of the null space.
Null space is defined for a vector, or null space is defined for a matrix. That's a
Okay,
different can of worms.
okay.
We will open it eventually, maybe towards the end of this course, but null space is a vector space, or null space is a vector
Yes.
space. That's that definition is slightly more involved, so I won't go into here because then I have to define a matrix and define its column space and all. So let's not go over there. So fine. So the finite
Okay,
sum
sir.
is called right. This is what you have done till now. Yes. So it's called a linear combination of V1 to Vn. And a set of now continuing our discussion about vector spaces. A set of vectors V1 to Vn spans V and is called a spanning set of V if V for all, or if for all V in V, we can express V as a right. This is the definition of spanning set.
Yes, sir.
And vector space V is finite if it if can be spanned by a finite set of. Agreed? Or this is the definition actually. You don't need to agree with this. This is the definition. And a set of vectors Vn is dependent if summation I equal to 1 to n alpha I pi equal to the all zero vector for some alpha 1 to alpha n in F such that alpha 1 to alpha n are not all 0. Fine. Linear dependence. Equivalently, Vk equals 1 over alpha k minus 1 over alpha k, actually summation j not equal to k, or I not equal to k, alpha I Vi. Right?
Yes, sir.
Great. So based on this, we call a set of vectors v1 to vn as linearly independent if it is not fine. So what is linearly independent? Something that is not linearly dependent. Trivial definition, but we need to define linear dependence carefully for that. So a set of vectors v1, vn is called basis of v, called a basis of v if it spans v and is the remember.
Yes, sir.
Anyone else except Rahul? Remember this?
Yes, sir.
Yes.
Yeah. And is linearly independent. And in other words, a basis, or let me, if v1 to vm span v but are linearly dependent, then there exists a subset of v1 to vm, subset vm to v of, or there exists a subset of v1 to vn, because we don't have to include one. That definition would subset of vm to vm that forms basis of. Similarly, if v1 to vm are linearly independent but do not span v, then a superset v sorry, a superset of v1 to vm forms the basis. Fine. And consequently, the basis is the maximally linearly independent and minimally spanning set of a vector space. Fine. So far, so good.
Yes, sir.
Yeah, if you have slept off, then this is the tip of the iceberg. The Titanic will sink this way. Yeah. Dimension we define the dimension of a vector space as the cardinality Makes sense?
Yes, sir.
And this is just a statement. We are not doing a formal proof. Any vector space can be seen as a version of right?
You mean subset of this?
No, as a version of this, not a subset.
I mean,
Any n-dimensional vector space, you can express it in terms of Rn or Cn.
okay. Yeah.
Makes sense.
Yes,
You
sir.
can reduce any n-dimensional vector space to Rn or Cn.
O of n, sorry, zero n dimensional zero vector would form a vector space, would should be a subset of it, right?
No, no. So zero dimension. So the trivial vector space is zero dimensional.
No, but anything multiplied by zero added to like with on a vector space having only zero but n dimensional of like
No,
zero.
so a vector. See, what you are talking about is a n tuple with all zeros, right?
Yes.
I'm not talking about a vector space with n dimensions. I'm talking about an n-tuple with n zeros, or an n-tuple with all the entries being zero, right?
Yes.
And it's defined over the field of complex numbers, right?
Okay, sir. Yes, sir.
So the spanning set. So there is no spanning set here because there is no linear. It contains no linearly independent vectors. Bhavnik?
Yeah.
So the all zero space contains no linearly independent vector, so it's zero dimensional space.
Okay. Yes. Okay,
Trivial.
makes sense.
That's why it's called it is called a trivial vector space. So now instead consider this n tuple. So fine. How many? 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. So 7 ones. So consider this vector. So alpha, let's call this E. So alpha E will always be in of this form. So though this is a 7 tuple, so this is contained in R7, but or even C7, but I can represent any entry using C1. I know just that I have to simply repeat that entry 7 times. Fine.
Yes, sir. Got it.
Yeah. So see, this is a tuple, not a vector. There's a subtle difference between the two. So this is a 7 tuple, not a length 7 vector. This will become a length 7 vector when it comes from a 7-dimensional vector space.
Sir, could you
So this,
explain this again?
sorry,
Um, So what's the difference between the only difference between a tuple and a vector is that a vector comes from a n-dimensional vector space.
No. So anything can be a vector. So if you go back to the top, so a vector space is a set of elements called vectors. We haven't defined, we haven't necessarily said that these elements should be necessarily tuples.
Okay.
And since I wanted to save this example for the end, but seeing that you are confused, let's now with here consider the set of finite energy waveforms over the field C. Let's now consider the set of finite energy waveforms over the field C. So I have a finite energy waveform. Let's say Vt is a finite energy waveform. What does a finite energy? What does this mean? That Vt V implies V square t, or the absolute value of V square t integral minus infinity to infinity dt is some m which is strictly less than infinity. This is the definition of a finite energy waveform.
Yes, sir.
So now consider two finite energy waveforms U and V. Ut and Vt. So define Wt equals Ut plus Vt. Fine. I can do that.
Yes, sir.
So does this satisfy closure? If Ut and Vt are finite energy, then is Wt finite energy? If Ut and Vt are finite energy, is Wt finite energy?
Yes, sir.
Yes, the maximum energy can be, from what we know, the maximum energy can be 4 times the, or the maximum energy can be a square plus b square plus 2ab.
Yeah, we can also use Cauchy, I think.
Yes, we can use all of that. Actually comes from vector or seeing finite energy signals as vectors. So that's the consequence. So this so the set of finite energy waveforms over the complex field or over the field of complex numbers satisfies closure.
Yes, sir.
You can also say that it satisfies associativity. Sorry, commutativity and associativity.
Yes, sir.
There exists an all constant zero DC signal, which if you add to any waveform, the waveform will remain unchanged.
Yes, sir.
So for finite energy waveforms, commutativity is satisfied, associativity is satisfied. There exists zero, and obviously there exists minus of Vt.
Yes, sir.
So all the properties of waveform satisfies all the properties of addition, and you multiply a waveform with a scalar, it satisfies obviously a finite scalar. It satisfies closure over uh, um, scalar multiplication.
Yes, sir.
Yes, sir.
So it satisfies closure over scalar multiplication. Check. It satisfies associativity over multiplication.
Yes, sir.
Check. Multiplicative identity. Check. Distribution over addition, distribution over multiplication. All of it are satisfied.
Yes, sir.
So, and the signal DC signal xt is equal to 0 is a trivial vector space. So you can say that you can say that the finite energy, or the set of finite energy signals over the field of complex numbers is a vector space.
Yes,
Yes,
sir.
sir.
Right. So the set of finite energy waveforms, or the set of finite energy signals over the field of complex numbers is a vector space. It does not consist of tuples. But we will eventually end up showing that these waveforms can be represented as tuples. And this is what allows digital communication. So viewing signals as vectors is called the signal space representation of, or you viewing signals in a vector space is called the signal space representation.
Sir,
Yeah.
sir, a vector space need not be finite dimensional.
Yes. But
Okay.
we can conveniently, so for finite energy signals, we can conveniently reduce those to finite dimensions.
Okay, sir.
Okay, okay. So another kind of mental experiment or thought experiment that I'm giving you is uh, the set of periodic signals is also a vector space, not a finite dimensional one. You can do this thought experiment, or you can try out this thought experiment yourself, that the set of periodic signals is also a vector space. Do you agree on that?
Yes, sir.
So the sum of any two periodic signals will be periodic,
Yes, sir.
and so on. That's not a finite dimensional vector space, and you can actually reduce it to the Fourier series representation is actually reduction of that finite dimensional vector space to something of an analog of uh, uh, or
Yes.
an infinite or infinite. So you are basically reducing that to a sequence. That's not a finite dimension. So you are reducing that infinite dimensional vector space to an infinite sequence. Finite energy signals won't be so problematic. We can reduce. We'll show that we will reduce this to these two finite dimensional waveforms. Fine. So the last point that we covered was that any n-dimensional vector space can be viewed as a version of Rn or Cn. So the next topic is inner product spaces. So I think we should stop here. Anyway, we are kind of out of time. So we'll stop here and continue on Tuesday. Or let me just do one more thing, since we have 2 more minutes. Let me do one more thing and define the notion of an inner product. So an inner product on a complex vector space V is a complex valued function of two vectors u and v denoted by that satisfies u v alpha u alpha sorry u comma w, not u comma v, beta v comma w, and
Sir, inner product of UV equal to VU conjugate, no?
sorry vu conjugate, sorry. Zero only if v equals 0. Fine. So we stop here and continue with the inner products. A vector space satisfying the above axioms is called an inner product space. Vector space satisfying these axioms called an inner product space. Full stop. So we stop here and we'll continue on Tuesday. Fine.
Okay, sir.
Okay. Bye.
Bye, sir.
Have a
Thank you.
nice
Bye, sir.
weekend, all of you.
Bye, sir.
Bye, sir.